Suppose you ask a robot to move a box from room A into room B. First, that sounds almost trivial. The robot sees the box, so it grabs the box. That seems like progress. But now it reaches the door and gets stuck. In this world, opening the door requires an empty hand. So the robot made a move that looks sensible in the moment, but that move destroyed its ability to finish the task. This is the central motivation for automated planning. Intelligent behavior is not just about choosing a good next move. It is about choosing a move whose consequences are also good. A reactive agent responds to what is true now. A planning agent reasons about what could become true later. That is the difference we are going to build for the rest of this lecture. Before an AI can plan, it needs a language for describing the world. In automated planning, that language is usually built from predicates. A predicate is a symbolic statement that can be true or false. For example, a statement like at XY says that object X is at location Y. A statement like holding X says the robot is holding X. A statement like open D says door D is open. These are not full natural language sentences. They are compact symbols the planner can reason with. Now look at our little world. We can turn the scene into concrete facts. The robot is in room A. The box is in room A. The door is closed. And the robot has an empty hand. This is the crucial move in planning. We convert a messy physical situation into a symbolic model. Once that conversion is done, the planner can reason on the symbols instead of on raw reality. Now we can define one of the most important ideas in planning, the state. A state is the set of predicates that are currently true. In other words, a state is a symbolic snapshot of the world at one moment. If the door is closed, that fact is in the state. If the hand is empty, that fact is in the state. If the robot later opens the door, the state changes because the set of true predicates changes. Next comes the goal. And the goal is usually smaller than a full state. We do not always care about every future detail. We only care about the facts that define success. In our example, success means the box ends up in room B. That is enough to specify the goal. Put these pieces together and we get a planning problem. An initial state, a goal, and a collection of actions the planner is allowed to use. This is the object the planning algorithm will solve. So how does the planner move from one state to another? Through actions. An action is a transformation rule. But an action is never just a name. It has structure. First, preconditions. These are the facts that must already be true before the action is allowed. Second, effects. These are the facts that change when the action happens. Watch the action open door. It requires that the robot is in room A, the door is closed, and the hand is empty. When those preconditions hold, the action can fire. Its effects then rewrite the world model. Closed door disappears. Open door appears. That is already enough to show an important principle. Planning does not update the world continuously and vaguely. It updates the world symbolically, through explicit action effects. Now consider pickup box. This one is even more revealing. If the robot picks up the box, then holding box becomes true. But hand empty must stop being true. And the fact at box room it must also stop being true. This is why add effects and delete effects matter. Actions do not merely add information. They replace one symbolic situation with another. Now we can describe planning more dynamically. Start in the initial state. Apply an action. You get a successor state. Apply another action. You get another successor state. Each of these steps is a state transition. If we string the right transitions together, we eventually reach a state that satisfies the goal. But the planner does not only consider one transition sequence. It can branch. For example, what if the robot picks up the box first? That creates a different future state. In that future, the hand is no longer empty. So now open door may be impossible. That branch is a dead end. Another branch opens the door first. That branch stays alive. Then the planner can pick up the box. Then move the box. Then reach the goal. This is why planning feels intelligent. The physical robot does not need to make all these mistakes in the real world. The planner can explore them symbolically in advance. At this point, the basic idea sounds manageable, but planning becomes difficult extremely quickly. Why? Because even a small symbolic world can generate many possible states. As we add more predicates, the number of possible truth assignments grows rapidly. Not every combination is legal, of course, but the number of candidate states still becomes large very fast. Then the problem gets harder again when actions create branching futures. From one state, the planner may have several actions it could try. From each of those successor states, it may again have several actions. After only a few steps, the planner is facing a huge web of possibilities. This is the state space. Each node is one possible state of the world. Each edge is an action that can transform one state into another. Somewhere in that space is a goal state. The planner's challenge is to find a path to it, without getting lost in the combinatorial explosion. Now we can finally state the planner's objective cleanly. Given an initial state, a goal, and a set of actions, find a valid sequence of actions that transforms the initial state into a state satisfying the goal. That is the foundational planning problem. To get there, we built a chain of ideas. Predicates give us symbolic facts. States collect the facts that are true now. Goals specify the facts we want to make true. Actions tell us how the world can change. Preconditions tell us when an action is legal. Effects tell us what the action changes. State transitions connect one symbolic world to the next. And the planner searches through this state space for a path to success. In the next video, we will sharpen this representation further and ask a more subtle question. How do planners represent change efficiently without having to describe the entire universe every time an action happens?